All right. Well, good morning, everybody, in person and online, to the latest installment of the Bureau Seminar Series. It's my pleasure today to introduce Chen. Anne has more than 15 years of experience in SAR and InSar algorithm design for Earth system science applications. In 2017, she joined the Department of Aerospace Engineering and Engineering Mechanics at the University of Texas at Austin. Since 2018, she has also served as a faculty member, by courtesy, in the Department of Geological Sciences at UT Austin. She currently leads the Radar Interferometry Group, housed in the Center for Space Research. Her group focuses on the development of new satellites and especially interferometric synthetic aperture radar, or InSar techniques. Say that 5 times fast. She uses these for studying natural and induced seismicity, groundwater resources, natural disasters, and permafrost hydrology and carbon storage. She is a senior member of IEEE. So I think it should be an interesting talk. Thanks everybody for coming, and I'll hand it over to Anne.
That on? Okay. It measures the Earth's different property of the Earth from the space. And one of the very first example is actually just a photo that was taken from the Apollo mission. You send the astronaut go to the space and you take a picture of the Earth, and it's going to be very different a perspective from the picture you would take on the Earth itself. And of course, we do not have to always send astronauts. We can put sensors on the satellite and making different measurements. And so people have been sending out optical imageries. And so that's Landsat mission, and also have those GRACE mission for measuring the Earth's gravity field. And in my particular specialty, we focus on imaging radar, and another way to say it is a SAR, or synthetic aperture radar, that works as follows. So at time 1, the satellite will fly over an area of interest, and it will look sideways with a roughly look angle from the vertical direction to the side about 30 degrees. And periodically, it will emit pulses that will illuminate a swath of the Earth that was illustrated in yellow here. And typically, in those kind of geometry, the swath width is tens of kilometers to hundreds of kilometers. That allows this type of techniques to cover a very large swath just in a single map. Single flight, and make it possible to cover the entire globe within like a short revisit cycle. So the pulses will travel along what we call the radar line of sight direction, and at every ground pixel location, and we're talking about the spatial resolution at meter level, so those ground pixels are meters apart. So every ground pixel location, they will return 2 pieces of information that will later be received by the radar satellite. The first information is the amplitude information. That it tells you how bright, how much energy that ground scatter returned to the satellite. And if we put the amplitude information from different pixels together, we get an image of the ground. It's a grayscale image. Kind of looks like the grayscale optical image, but because they are different sensors, they are sensitive to different things and contain different information. And people like radar imaging because it's an active sensor, so it doesn't need illumination from the sun. It works during the day and the night, and also it sees through the cloud. And so that makes it suitable for like some of the emergency response purpose for some extreme weather application. So for a long time, people use this amplitude information to get an understanding of what is happening on the Earth. People use that to track the glacier movement, the retrieve of the grounding line, or how big the city has been like changing over time. Like you can actually visibly see the offset have grown over many times. And also the second piece of information is this phase information. But for a long time, because within each of the radar pixel, the radar scatters usually interact with the radar at a comparable wavelength, that's a centimeter level. So there are many of those small scatters, and each of them will reflect the echo. And the phase you have received is a combined return from all those scatters. And because of those ground scatters and how they distributed random, so for a long time, people say, well, there's not much information from the phase, and let's just use the amplitude information. But interestingly, and if you have the same satellite fly over the same area over another period of time and make an almost identical measurement, so a slightly different position. So we're talking about these two satellites are almost like in a frozen orbit that is about 10 to 100 meters apart in the second time. And so if you could acquire another radar image of the same area, and you calculate the phase difference between these two radar positions, if the ground scatter doesn't change much between these two acquisition time remains stable, so their net random effect got canceled. So suddenly, those phase difference that no longer looks random and it looks like pretty fringes that contain some piece of information. We know the satellite position accurately, so we can actually, based on the satellite in geometry and derive the observed phase is actually related to the Earth's topography and a centimeter to millimeter level surface deformation. So InSar is a technique for mapping surface topography and surface deformation. And we have such data available since the 90s. So the earlier mission that was launched prior to 2010, and you can see that it was showing below the grayscale line. And so those data lists generally have open data policy. You don't have to pay to get those data. Those earlier missions usually revisit the same area of the interest every 35 to 46 days. And often those earlier missions, they might have some acquisition gaps, so they don't always successfully collect data at each revisit cycle. And so that usually leads to maybe tens or hundreds of interferograms for a particular case analysis. And so things has actually changed dramatically over the last 10 days. Since the launch of the Sentinel-1 mission, and so we actually have the global coverage of such data at every 6 to 12 days. And so, and those data are open and totally free, and they are just for anyone to use. And so the change between tens of hundreds of interferograms to now routinely we're analyzing thousands or 10,000 of interferograms allows us to utilize a lot of big data analysis strategy or statistic, machine learning to really improve the signal to noise ratio and detect things we used to not be able to detect when you have noisy measurement. If you have 10 of the same noisy measurement, even a simple average will give you a much better observation than just a single data alone. So that's what happens in this area. And another exciting thing we're going to talk about is although InSar techniques was developed actually at NASA JPL in the late 70s, early 80s. And so NASA cannot get a funded InSar mission because of it's a relatively large budget. So all of those missions listed here are launched by foreign space agencies. So ERS-1, ERS-2, NISAR was from ESA, and Sentinel-1 is also from ESA. So they have been doing this for quite a while and have a huge success. And so ALOS is from the Japanese Space Agency, ALOS-2, and TerraX is from the German Space Agency. So, but the very first NASA-led InSar-based mission that is in partnership with Indian Space Agency, it has been underdeveloped for the last 10 years and expect to launch next year in early February. So this is going to be an exciting period because this mission really learned from all those past missions. And once the NISAR mission is launched, we expect another dramatic increase of the data volume and data quality. And also, because it's a NASA-led mission, the mission budget is over $1 billion. So once we have the data available, they actually going to also have a research program that calls to maximize the mission impact and utilize the mission. So we anticipate this is a really, really good time for InSar research. The data are there, and there's a lot of, and every time when there's a new technology, a new data, there will lead to new science discovery. So I'm really excited about that. So what InSar can do, I often say, well, I work on data processing, but it just never ends at the data itself. And what we care is what we can learn about the Earth's surface and interior. So people have been using InSar for study earthquake and volcanic deformation from the early 90s. And recently, more increasingly, because the data quality are getting better, people are starting to be able to accurately monitor much smaller signal, like a silent earthquake that people don't even feel with millimeter level deformation, or study coastal deformation. And I have an active ongoing project with UTBEG to study the amount of deformation we can see in West Texas due to oil and gas exploration. And those kind of data are now routinely delivered to the stakeholder for hazard monitoring and operational kind of safety monitoring of the reservoir. And another kind of interesting example is that also recently our group also started using InSar measurement for studying the permafrost on the north slope of Alaska. So I was a remote sensing person. So most of my work in the earlier time was standing in front of a computer. Remote sensing, you don't actually have to go there. But through this permafrost project, I actually really appreciate I was able to go there to collect data in those rural areas. So really pretty place. You went there once, you want to go back and try to learn more about it. So the reason InSar actually is capable to help out to scale up those in situ measurement is that when the permafrost thaws in the top layer of the permafrost, that's what we call the active layer, they thaw in the summer, and then when the ice to water phase change will lead to a volume change, and that's accordingly we will see a thaw subsidence in the summer. And then also there's the active layer refreeze in the winter, you're actually going to see that uplift. And the amount of those thaw subsidence and active uplift can be detected by InSar, and in turn can help you to monitor how much water has thawed in that time, and also help you if like the permafrost deepening with additional thaw, you would actually see a lot of trend, and in area that is wetter, you actually see a larger seasonal variation. So there's a lot of rich information that is linked to that. And because those active layer, the water in the active layer actually is a very important media. Like when you see those active layer water, it's like you're putting a tea bag in a cup of water. So they have a lot of organic matter in it, and the organic matter will source here and move around into the rivers, to the ocean. And it's very important to be able to understand this quantity, how much water are there moving around in order to better constrain the carbon budget near the north slope of Alaska. And so also people have been studying groundwater aquifer depletion. So recently we are like collaborating with the UTIG and also Odin Institute, trying to use the InSar surface deformation data, trying to better invert through a poroelastic media and a Bayesian inversion, trying to better understand the permeability of the subsurface field. And in this way, and we can understand where there's like a high permeable fluid channel where you have a fluid barrier. So I find it's like a work is interdisciplinary by nature, and I'm well positioned to work with a lot of people here at the BEG and UTIG. So this is a really good place for me to work with everyone here and trying to everyone will contribute to the puzzle and the piece of the puzzle, and we can together solve the problem. So for the rest of the talk, I'm going to focus on one problem that many of us actually cares about, that is coastal flooding, coastal subsidence along the Gulf Coast. So I want to start this portion of the talk by a small community called Brownwood that was developed in the late 30s. And in 1944, when the community was first established, it was near the ocean. It was a highly desirable neighborhood. So people were very excited about that. But typically, things are slower over time. People start to realize that, like by the time of 1981, there are lots of like repeated flooding that seem to like over time increase in severity and magnitude. And by 1978, and people start to realize a lot of the land that was above the sea level by the time the community is built is already sink underneath the water, that is marked in blue here. So one of the stars here shows one of the famous photos right there. Back then, this house, when they were first built, they were 10 feet above the sea level. But by that time, it was already sitting under the water. And by today, no one there's no community there. So this actually become a educational area, a natural center for people to kind of understand the coastal subsidence and this kind of issue. And also we have seen this bar. So this is a way, if we don't use the satellite geometry, trying to move forward. So the satellite geometry trying to actually see the land subsidence from 1955 to 2021. So that's over 3 meters over the course of this long time. So it's actually a pretty small process compared to California, and people have been doing a similar kind of land subsidence in situ survey. So here shows in Central Valley, California, from 1995 to 1977, the subsidence due to excessive land pumping. However, it doesn't matter, like just because the subsidence is small, because our Gulf Coast, most of the community are sit right at the sea level. So it's actually very prone to land subsidence. Even 3 meters of subsidence over time can have a devastating effect on the community. And that's why we actually want to better understand the distribution of the subsidence and also its impact and its implication to future flood risk. So what is a key challenge here? So as I mentioned, a key challenge here is when you're working on any kind of in situ or remote sensing measurement, typically, even for the same, any of those measurements are gonna have some kind of noise level, right? And for InSar, the noise level vary depending on the study site. But in general, it's much easier to detect a larger signal than a smaller signal that is comparable with the noise level. Compared to California, where we have a lot of reported InSar study, the same analyze algorithm won't work just because in California, some region in Tulare Basin, we have several centimeters per year of deformation. But most of part of the Gulf Coast, even when those processes are clearly leads to subsidence, they are typically slow. They expect subsidence on the order of just a few millimeters per year. And to be able to actually capture them is actually super critical in order to actually predict the future landfall, because they're just so flat. They're already pretty much like maybe 1 meter or 2 above the sea level. And how are we going to be able to map the land subsidence? So besides InSar, there is actually a complementary approach that is using GPS. And here we are actually showing the amount of GPS permanent station along this area. So this is the initial area we're interested in, from Corpus Christi all the way to the New Orleans area. And we have close to about 200 GPS stations, and each station you have those GPS daily time series in the east, north, and the vertical direction. And you could they usually have those for over a very long period of time, for why we call it a permanent station. And typically by using those time series, you could extract the long-term subsidence rate from those measurement with a millimeter level of accuracy. So by just the first looking at it, we will see, well, there's quite a lot of stations, but it's actually, in fact, a huge area for only have about 200 point measurement. And one of the bigger issues is that a lot of those existing stations, their space distribution is not uniform. So you can see within Houston, because they have a lot of buildings, it's easy to put a GPS right on top of the building. So they have a relatively dense like GPS network within the Houston urban area. But once you go to those rural areas, especially right at the coast near those wetland region, there is actually not that many stations around. And so, and if you look at most of the stations, majority of them can just show you the land is not moving much at all. So, and is that really true? So we also have InSar. So I was talking about InSar, but here I would like to give you an example of what our data looks like. We don't have a time series. So what we have is a 2D deformation map. And here is one of the very first interferogram that was published at the cover of Nature right after the very first InSar mission, Sentinel-1, was launched. So what we're seeing here is this area covers 90 by 110 kilometer area that spans a major earthquake. So the first SAR acquisition was applied before the earthquake. And the second SAR acquisition, when they're making the phase difference, is right after the earthquake. And what you are showing here is a co-seismic deformation that was caused by the earthquake, where the dark black line shows the ruptured fault area. And so each of this color cycle from red to red or green to green corresponding to a phase cycle of 2 pi difference, and with corresponding to about 28 millimeter line of sight motion. So this was a big thing back then, because people has been using those crustal deformation model to predict those butterfly deformation patterns. However, no one are able to actually measure it with such detail using observation. And this is basically how we see an earthquake from space. Of course, another key challenge in here is, well, as I mentioned earlier, it's easier now to routinely detect earthquake, but our signal is much smaller, right? And those coastal deformation do not give you a magnitude Earth 8 or earthquake-like deformation pattern. And while the signal is small, and our noise level along the Gulf Coast is also huge, because one of the major InSar measurement source is actually tropospheric noise. And so which tends to be those air circulation, the variation, those kind of things would lead to centimeter level delay that is visible on your interferogram. And so you can even see a little bit of the things here, like those are variations. Some of them are due to troposphere, but because of earthquake deformation is so high that you don't get distracted. But if you're looking at a Gulf Coast interferogram, first order, all the fringes you can see, it's probably due to tropospheric noise because it's humid and it's hot. And so this was like the worst case scenario for tropospheric noise measurement. So we're talking about estimating something millimeter level, like a few millimeters per year, but at the same time, you might subject to like 30 centimeters of tropospheric noise. So Texas, tropospheric noise, West Texas, when there's a heat wave and they have a lot of energy in the atmosphere, and you definitely see these signatures. So what can we do? And people have been working on that for a long time. So one of the important things for my PhD study is actually trying to develop ways to mitigate tropospheric noise. And here is the image of the silent earthquake in Hawaii, Kilauea, south flank of Kilauea. And we proved that with a dedicated imaging mitigation strategy, you actually can achieve millimeter level error. And as we said, like Hawaii is also a tropical island, so hot and humid environment. But it's actually pretty sad. Like back then, I spent like 3 years to get this one final map that has a very good accuracy. But shortly after I graduated, after the launch of the Sentinel-1 mission, I realized that all the technical development work I developed during the PhD is no longer needed. And so the key idea here is back then we have like tens to hundreds of interferograms, but after you have a launch of Sentinel data, when you have thousands and 10,000s of interferograms, those tropospheric noise from day 1 to day 2, and usually they're not correlated. Just like we don't actually know today sunny has nothing to do with the next day, next week, whether you get a rainy day or a sunny day. So when you have a lot of those noisy measurements, and you can actually just mitigate the tropospheric noise by average them out. And another thing we find recently is that the tropospheric noise also has those outliers. And that means there's probably a particular bad stormy day or particular bad day when there's a big heat wave. And it used to be if you have a small amount of data, every data point is precious and you use all of them. But now you have a lot of them. So we actually can afford to throw away this 10% of extreme weather day and then use a very simple strategy to process the InSar data and have much better results than our PhD study 3 years ago. So now we actually, more data actually makes the processing analysis a lot easier. Unfortunately, there is one still big challenge, even with all those advances. Gulf Coast is still one of the most challenging InSar processing scenario. Is that besides the tropospheric noise, another challenging scenario is also InSar technology works. So it has a critical assumption that surface stays about the same. So from day 1 to day 2, if like there are trees and the tree leaf falls, they actually leads to a lot of random signals that are going to corrupt your signal. So this technology doesn't work very well in area with rapid surface change. Typically, a scenario would be vegetation and the vegetation change. So here is an early work for InSar subsidence mapping in Houston area. As you can see, in the Houston there is a huge subsidence ball due to the groundwater pumping in the Harris County, and this was detected in the 90s. But once you're going beyond the Houston area, once you move to the suburban area where there are more trees, in the downtown area of Houston, it's all concrete. So those concrete doesn't change from over time. So the InSar works really well here. But once you move away from that area, you can see the coverage becomes spotty. It doesn't mean we don't have data. It's just the data quality is bad and people have to mask it out. And there are some more recent development. So since 1990s, people have been working on this problem. So this is one of the more recently published land subsidence paper along the Gulf Coast. And you can see by looking at it, there are some localized hotspot, but a lot of the area is green. Looks like we don't detect anything. And if you're looking at the RMSE error between InSar and the GPS, their order is on the order of centimeter a year. And earlier we mentioned our expected signal is actually probably a lot of the case, it's only a few millimeter a year. So if you have an uncertainty agreement at a centimeter a year, essentially your signal is below your noise level. And ever since then, there were several papers published in this domain. But from study to study, a lot of these patterns, even they're derived from the same data, do not look the same. So there is a call for like understanding the method and probably develop a more independent validation strategy to better understand what we can measure and what's the true subsidence signal looks like. So here, give you an example of what the interferogram looks like in the Gulf Coast. So this is an Sentinel-1 interferogram over the Houston area. And in those middle area, that's the downtown area of Houston, where you have those coherent phase, where you have those phase information contain tropospheric noise and also surface deformation. But once you're outside of those area, you can see the phase essentially because of those vegetation effects become random and they don't contain useful information. Traditionally, we throw them away and only focus on the data that is coherent. But the problem is once you're in those suburban area, you throw away too many interferogram and then you end up putting a mitigated tropospheric noise. That's another problem. You go back and you need many, many interferogram to average to get rid of the tropospheric noise. But if you have trees, you end up, even there are a lot of data, most of them have to throw away. So what can we do? It turns out, even in those decorrelated region, our eyes couldn't see any coherent signal. There are actually lots of these point scatters, what we call the persistent scatters that exist. So in the San Luis Valley, where you see the agricultural field, the Central Valley pivot system for conserving the water leave those unvegetated area between those agriculture circles. And using a detection algorithm, you could actually find those high quality data and focused on only use those radar measurement for surface deformation analysis. Even in the Gulf Coast, we do not have this central pivot irrigation system. We actually still have a man-made road, a shed, even a rock. So if we can detect them, there are still going to be more of those stable pixels than just the 200 GPS stations. So that's an interesting idea. How are we going to be able to detect this area? So if you're detecting it, then we can actually just employ interpolation using this high quality measurement. Here, what we show is in the middle yellow is a pixel of interest that is decorrelated. And if you have a area and just look at the surrounding high quality pixels that marked in red, and you could use a weighted sum to replace the center pixel with a high quality measurement. And so here is what we see. So this is that San Luis Valley area. And if you zoom into the agriculture area, you can see all those circles. Agricultural circles essentially has a random phase measurement, but you also see those coherent measurement in between the circles that are corresponding to those optical images. And after this interpolation with this high quality data, and you can see the phase continuity was reconstructed. And you start to also see some fainted, like a smaller uplift signal that was not that easily visible from the earlier data. So this was actually consistent with a lot of the groundwater well measurement on the water fluctuation. So it looks like this type of technique, the critical thing in order for the interpolation to work is to be able to detect a dense enough of high quality pixel. So if you don't have many high quality pixel, that won't work. So how are we going to do that? It turned out to be one of the foundational problems in the InSar, like radar interferometric theory. So a lot of the existing approach, and people have been working on this since the beginning of InSar. So if you want truly global coverage, you know, lots of trees everywhere. So this is an issue. And so the earlier mission, they're usually based on radar scattering models. So they're usually rely on some oversimplified assumption. For example, trying to model the radar return as like a Gaussian IID random circular models. And then even with those oversimplified assumptions, here is the expected phase distribution as a function of signal to clutter ratio, like high signal to clutter ratio usually means a more stable signal. It's very complicated, right? And so now when people are trying to extend this theory, they start to find a more realistic radar signal scattering model do not have a closed analytical form. So kind of people have been stuck here a long time. And using a lot of those existing models for persistent scatter detection, we just don't end up having enough for the Gulf Coast for any reasonable analysis. So our group recently think, well, if the model approach kind of got stuck, right, because we don't have a realistic model, they don't have a derived form. And now we have a lot of data. Is it possible to derive some data-driven approach to detect those high-quality pixels? So we actually got an idea from a simple computer science class that's called the cosine similarity, because in computer science, a lot of the time you would like to find things are similar. Amazon wants to find similar customers, right? And Google might want to find like the Netflix might want to find people like similar movies, or the similar movie that might be liked by people. So this is a very common problem, people trying to find similar data points. And as we think about our radar data, those are coherent signals, when they are spatially coherent, they're similar to each other. While those incoherent signals, they look like random things, and they're not similar to each other at all. And so in the 2D, the cosine similarity is one of the measures that we can actually quantify two vectors are similar or not. It works like follows. So we all see this cosine similarity. So if you have a two vector A and B in the 2D space, their angle theta can be written to inner product of a vector A and B, and then normalized by its amplitude. And so that cosine theta formula allows you to actually calculate the theta between these two angles. So like I didn't realize this is actually a similarity measure until a very later time, because if you're thinking of that, when cosine theta equals 1, that means the theta equals 0. It means these two vectors are pointing to the same direction. They're similar, right? And when cosine theta equals 0, and that means theta equals 90 degrees. And that means the vector A and B are orthogonal, right? And that means they are not similar at all. In the 2D, if they're orthogonal, like when one thing is changing in one direction, has nothing to do with the other direction. So they're like zero similarity. And so when cosine theta equals -1, right? And the theta equals pi, and this means actually they're anti-correlated. -1 means if A goes this direction, B goes to the opposite direction, right? So that's actually a way, just the simple measure, it's very easy to calculate, actually tells you how similar this two vector is. And the interesting thing is this cosine similarity formula works for high dimensional data. So this A and B vector do not only need to contain two numbers, they can have a many numbers. And you could imagine this vector A is all the InSar phase measurements from multiple interferogram at a given pixel. And B is another InSar phase vector at a nearby pixel that may be from thousands of interferogram. And then just by calculate their cosine similarity, be able to pick up those ones that are similar. And we think this is a good idea, but then when you work with big data, it ran into a big issue, is that we are working with a high resolution data. And when you have to find the similarity between each pairs, and you were thinking of like, we're just doing a very typical order analysis. We want to map the entire Gulf Coast. So let's just see what's going to happen even just for 2000 by 2000 pixel Houston area. So the number of pairs we need to compare nearly reach to 15 billion. So that's actually just not even possible. Like my student want to graduate in 5 years. So we have to figure out some way, not just waiting this comparison to be done. And so here then, like we kind of get inspired by when the people trying to reduce the number of computation. The key idea is we don't actually have to compare all the pair, how they're similar. So we can actually focus on the pair that is more likely to be similar. And the algorithm works as follows. So at the step 1, we are trying to start with guess instead of just trying to start to compute every pair. So there are lots of existing algorithms, right? And so they don't give you the accurate detection, but you can start with some candidate pixels. And you can even lower their selection threshold. It's just they might not be all right? And so you could start with a set of candidate pixels using any of the existing PS methods. And the step 2 is at every PS pixel that we have seen, some of them might be actually wrong because they are actually not similar to their neighbors. So we are actually at every PS pixel, that's a much smaller subset of, we look their surrounding neighbor that is currently marked as PS and calculated whether it's a higher chance for it to be a false positive detection. And those red ones are the ones we actually removed. And the third step is then at every non-PS pixels, and we actually look around for its PS neighbors and to compare the similarity between them. And if they are actually similar, we added back that we marked as the previously false positive detection. Those are the green ones. And because this algorithm started with the existing approach, it removed the false positive, it adds back the false negative, so they're guaranteed to at least do better than whatever you have to start with. And this is really exciting because once we have this detected, NLPS interpolation works like almost like a magic. And at that time, I was very excited when the student actually resolved that. And we actually used all the, because Houston area has a lot of GPS stations, we use the GPS, the tropospheric resilience delay estimate, plus the deformation estimate to validate these fringes. And we find this PS interpolation really improves the consistency between the GS predicted tropospheric noise plus deformation signal, plus what we are seeing in those covariant InSar measurements. So in this case, once the decorrelation is fixed, the tropospheric noise is the dominant component. That's mostly what we're seeing here, those water vapor gradient, plus that noise deformation feature that are due to the Harris County groundwater. So here we apply to this area and it's promising, and we can see on the left is without PS processing, on the right is with PS processing. The first step is that they actually look similar, and that's actually in a lot of the area. That's expected because where you see the biggest subsidence feature, that's in Houston area. This area doesn't have a decorrelation, so our PS processing algorithm should actually retain the same feature from the existing classic algorithm. And the huge difference actually comes on this coastal region. Here we zoom into a region near the Galveston area. And without the PS processing, when you're just trying to use random phase vector to solve deformation, you tend to get a near zero measurement. In fact, they have a slightly blue hint that even predicts some uplift here. However, with PS processing, we actually see there is actually indeed some subsidence feature we had detected. And one of the convincing thing is before those triangles are GPS validation station where blue white means a good agreement. And it looks like those kind of detection really start to extract the true signal that is detected like independently with the GPS observation. So we got something that seemed to work well, and so let's scale up because now the trend is we probably care about like large scale mapping along the entire Gulf Coast. But just like all the other research, every time you think you solve something, you scale up and it doesn't work. And so what we have found in a lot of the Gulf Coast, they have those very highly like turbulent tropospheric variation. Sometimes it can be very hard to capture just through interpolation of a finite number of pixels. And of course, we don't just stop there. When the interpolation failed, recently, we based on what we have learned and we use another phase reconstruction algorithm. It works so well, we decided we need to give it a name and to release the software package. It's based on eigenvalue decomposition, classic optimization method. So we call it the InSar algorithm. And so for the same area, you can see it actually starts to recover those turbulence noise, which were validated again using a large number of GPS data. And that really is a step forward. Using this algorithm, we actually detected a big map. This is along over 1,000 kilometer Gulf Coast. And usually what our idea is if it has been tested over a large area, it usually works well in similar settings. So we are looking forward to continue to expand, but of course, there are going to be lessons to learn, then there is a potential future improvement. So the interesting thing is we did detect this Houston subsidence feature that was long detected, but also a lot of those coastal subsidence near the coastal area where you have a lot of dense vegetation. This map actually is the first time reported those signatures. Let's zoom into an example here. And here is near the Chambers County, and actually the Houston Subsidence District actually did an intensive GPS survey, and we can see the GPS spot is right here, here, and here. There are 3 spots and 4 spots right here. And they actually released a conclusion that there's no subsidence in the Chambers County. Our data actually agree with what their GPS data are. But the problem, if you only try to drop 4 dots over an area, it's very hard to actually capture those subsidence hotspots. So what we have seen is this area actually subsiding at about up to 1.5 centimeters per year. So it's actually one of the relatively higher magnitude of subsidence. And those subsidence actually in Texas or in California, a lot of those subsidence was actually due to groundwater pumping. But in Texas, it's actually not always the case because that Harris County 90s big subsidence ball draw a lot of public attention, and ever since then, they actually has been regulated groundwater pumping across those areas because they're concerned about subsidence. And from the 90s, Houston area subsidence to what we have seen right now, because of this active measurement, you can actually see that Harris County's subsidence feature actually has a decreased magnitude in subsidence. So they're slowing down. But in this Gulf Coast area, although there is not a lot of groundwater pumping, they're regulated. There's no regulation on hydrocarbon production. So what you're seeing here, those blue triangles are actually oil and gas production wells. And here is what we found from the internet. We try to see what can cause the subsidence. Looks like they're very spatially clustered with our detected signature. Like there's a signature here, and wherever you have a cluster, they seem to have a subsidence feature around that. So that's what we have found. A lot of the features along the Texas coast are likely related to some of the hydrocarbon production. And another exciting thing is here, once we cover a large area, we actually used all GPS data as independent validation. So our solution never sees GPS data measurement, and because we cannot get a validation at every point, so we like to use them as independent, so we have a more trusting area without GPS. And those are the inland area where we typically think the vegetation decorrelation is not too bad, and we expect the performance is better. Unfortunately, most of the GPS is also in this area where InSar, like traditional InSar method works well. So there's only a few in the coastal area for the GPS validation. But an exciting thing about this InSar algorithm is with this phase reconstruction method, you really don't see that impact on vegetation in both of these 2 scenarios. So inland area, you have about 1.9 millimeter per year agreement accuracy on average. And here in coastal wetland, it's about 2.2 millimeter per year. So they're comparable. And when you're releasing those large-scale deformation maps, consistency in accuracy is actually important. Otherwise, the users can get confused very easily. So now we have this map, and we don't want to end just as a map. And we hope to see how this subsidence actually has implications to flooding. And currently, existing storm surge flooding risk analysis was done using those storm surge models, and UT Professor Clint Dolphin's group, and I was really excited to learn about their model and what the model can do. So one of the things I find is that the abstract model, they were running hours or days before the hurricane landfall to predict how bad this particular flood would be. And also they were used for future flood risk analysis because you could run synthetic scenario for future simulations for the same area for different hurricanes. And so using the InSar data is actually ideal because InSar has a 2-dimensional map with a spatial resolution on the order of 100 meters, usually the final deformation product. And they actually match the grid very nicely. So this grid also has this 10 meter to 100 meter level of grid space basing. So they're spatially matched and they can be integrated nicely for some future flood risk analysis. So the way we do that, once we have the subsidence data, is then we're going to use the subsidence data under the assumption if the subsidence continue without any change. So if people don't do anything, they continue the activity. And then some of the area, based on their current topography, will be sinking into the ocean, right? And so we're going to predict based on the land loss by the year of 2100 about the land loss due to the subsidence and as well as the absolute sea level rise. And that will lead to change in those model grid based on the sea level rise will change the free water surface elevation. topography, surface deformation will be used to update the topography and the bathymetry grid, and that will lead to change in the land loss, which also changes the friction of each grid cell, because when you have open water, there's not a lot of resistance, and when you have wetland, they have trees, they're considered as a relatively rough surface. So we have done that first over the Houston area, where we see those subsidence due to hydrocarbon production. And we run the reference scenario Ike using the storm surge model. And those were validated with all those in situ observations already. So what we are seeing here is the expected storm surge height at the peak time. And what we have done is we also incorporated the subsidence only and rerun the model. And this allows us to see where the things have been changed, like where you see a yellow color near where we see the subsidence is where the increase of the surface height, and those are shaded orange area is the newly flooded region. So in general, in this area, we see an average of 35 centimeters of subsidence by year 2100, and the average increase of the flood water would be 41 centimeters. And in that case, it's actually comparable, like when you think similar amount, and then you're expecting the flood is increasing similar amount. But it's not always the case. We also run the separate analysis by considering the absolutely sea level rise, as well as the combined effect of the relative sea level rise. And so what we have seen is that in the median projection, the ratio of the sea level rise will lead to about a 91 centimeter of sea level rise. And so when you combine these two effects, the average increase is 152 centimeter. So in this case, one thing that is interesting is kind of as predicted, when you run the simulation based on sea level rise only, subsidence only, and you combine their projected like water level rise, they're roughly about 152 centimeter. But if you're actually looking at each particular pixel, it actually finds the relationship between this sea level rise and subsidence. They're actually complex. They're not linear. And that actually relationship become more obvious for the New Orleans area, where in this area, the land surface is generally very flat. So even a little bit of subsidence can actually flood a huge area. Yeah. And so also these red lines are the levee system. So when you have this levee system, it actually also changes how the flood will go. So this is a reference scenario. And in this area, we actually have a very, very subtle subsidence. And in fact, in the New Orleans area, blue region actually even shows a subtle uplift of 2 centimeters per year, because the earlier ISRO survey shows that the city was subject to subsidence in 2010. And so they stopped it, and we actually see some of the recharge within the New Orleans city limit. But however, there are some subtle subsidence up to about 9 millimeters per year south of the New Orleans in those coastal wetland region. And so what we have found is that the subtle subsidence actually does matter. And so even just considering an average region of subsidence by the year of 2010, about just 11 centimeters, that's over many, many years. And that the land loss due to that subtle deformation can, alone without even considering the sea level rise, can lead to a substantial amount of flooding in a lot of areas, including the area that you can see in the New Orleans city region where you actually see uplift. And the reason because of that is because when you're thinking of where things going to flood it, it's not just the location of where you are, how much it goes up and down that matter. It's all the pixels that the hurricane goes through, how much resistance that you have, the trees they see along the path. So that's kind of illustrated the subsidence 2D mapping is really important. Not only you need to know your area that you're interested in, but also what is happening surrounding you. And we did the similar analysis here, also include the average sea level rise. And what we have found is that it's very interesting in the New Orleans area. The average subsidence by the year of 2100 is 11 centimeters. It's much smaller compared to 91 centimeters of sea level rise. But when you're considering these two factors alone, they actually lead to comparable inundated area. So in this area, it's really, really prone to subsidence. And we actually plot for each like a grid position, like the vertical land motion is a horizontal axis, and the vertical axis is actually change in the water depth. And you can see for the VLM only X case, there is actually a pretty strong linear relationship. But for the other case, even including X, so the relative sea level case, you can see just knowing the surface subsidence at that pixel alone will not be able to help you to predict the flood risk at a particular location. So the relationship is highly complex, and existing a lot of the flooding risk analysis method based on passive flood mapping. And so basically it's what we call a bathtub approach. And they use a topography map, and then they have the sea level rise, and they basically predict that they're going to fill the topography in the lowest area. And our study actually find that will likely lead to very inaccurate result. And what we have found is really you need the best observation integrated with some models that actually take into account of the physics to be able to have some more accurate prediction. And so this is my end of the talk, and I'm happy to take questions.
I personally thought that was very interesting, and good and bad. I had like several questions written down, and then you immediately answered them after I wrote them down. So, sign of a good talk. Anybody in person have any questions they'd like to ask? Yes.
I'm curious, in your storm surge model, what's the space resolution?
I think it depends in the location. Typically, I think there are storm surge modeler here, but if I recall correctly, in the coastal area, until towards there, the grid is finer because usually you're more concerned with the area right next to the ocean. But as you move inland, then the grid spacing becomes more sparse. So the densest area, I believe, is probably like it's a triangular mesh, about 15 meters. And so the native SAR resolution is 3 meters, but usually for the final deformation map, we have like 10 to 100 meters. A grid spacing everywhere. The storm surge meter is from like up to 15 meters, probably in some areas much larger grid space.
Gotcha. Thank you.
Let's see, anyone else? Yes.
Yeah. Great talk. Just out of curiosity, have you been able to look at any salt features, salt domes and things? Do those come up from the interferometry at all?
That would be interesting, but we haven't particularly focused on that. But I know some groups are very interested in that. But when I was looking at San Luis Valley area, my impression is that using InSar deformation map alone is probably very hard to monitor with salt dome because of the critical assumption that the surface remains stable, but for the salt domes, the surface continuously changing, and that would not lead to very coherent measurement. So the SAR amplitude image.
Yeah, the SAR amplitude. I was just curious if you could kind of detect that from the interferometry.
Yeah, I think the SAR amplitude would be a more feasible approach. Okay. Yeah, you can actually detect changes over them and where they have been.
Others? I have a question I'm storing, but I'll give first dibs to other folks. Okay, well, I'll jump in. So can you show that slide again that showed sort of the Houston area over toward Louisiana? It was kind of toward the end there. Yeah, that you were showing where the oil and gas.
Oh, this one? Yeah,
yeah, this one. And actually, you go back to this one.
It's a larger map.
So I'm sorry, I want to make sure I heard you correctly. So this is either not yet or very recently released?
Yeah, so we just published like last month. It's at JGL right now.
Yeah, that's really interesting because I know a lot of these areas very well, and the Houston and Galveston counties, right? We have this, you mentioned it, right? The Harris-Galveston Subsidence District, right, which was created specifically to manage and control subsidence in those areas. But that's just those two counties. So all of these other areas over here to the east, yeah, right, where you're seeing that subsidence,
yeah,
there are no managerial controls in those locations for that subsidence.
That probably even belongs to the state of Mississippi or Louisiana.
Yeah, some of it definitely over there toward the further east definitely does. But basically everything from here over to the Texas border, there's no managerial controls for subsidence there. And so that's kind of an interest. This map is sort of an interesting finding that might potentially suggest that we need some of those managerial controls. It's really interesting.
I think it's partially because previously the GPS measurements tend to be too sparse in those areas. So they might just did one survey or not, and they conclude we don't see anything. So
Yeah, that next slide, 37. I mean, wow, what a picture, right? Where you've got your GPS just happens to all be in the areas that aren't seeing a lot of change.
Yeah.
Like that's really interesting.
Yeah, our actually agree with them within like 2 millimeters per year. It's
Right.
just they just I think probably this can guide them for their future surveys where they need to go.
I think that's really interesting. Not so much of a question, more just an observation on how this work potentially, informs our groundwater management and planning in the state, which obviously I let me check. Let me double check to see online. Yes, I was particularly interested in the correlation between oil and gas production and subsidence. Oh, we were just talking about that. Do you have any information about injection of fluids and rebound of ground levels?
So for this particular area, by the time we were doing the analysis, we weren't able to get any production and injection data. But those well location was we just Googled, and it was actually there's an oil and gas company's website. They showed those locations. But David Morick, and he did a separate analysis using our data over this area and using correlates with the historical well data. And what we have found was pattern near the Galveston area south of Houston was likely very correlated with those oil and gas activity. So they're usually also find it with some of the vertical fault. So the pattern seem to correlate with the node geology. And also for the oil and gas production, like those are ongoing investigation. What we have find is those oil and gas production, some of the data, some of the well already no longer active, but they have a production history probably decades ago. And in those areas, in some of those regions, we still see subsidence. So there may be some committed subsidence. So once you have produced from the reservoir, they're not going to reach equilibrium right away. So even it can have continued subsidence even many years after they stop this activity.
Well, and the question was specifically also about injection. So you mentioned you were doing some work in West Texas, right, in Permian Basin and whatnot. So are you seeing sort of the opposite, right,
yes,
where the land surface is rising?
Yes, and so here, like we can see along the Gulf Coast, we actually only see very small uplift in the New Orleans area. So everywhere else is subsidence, but in West Texas, we actually see huge, rapidly developed uplift feature, and also the SMU, they recently also published a paper on the imperial area. So those injection definitely can, especially the shallow injection, can lead to rapid inflation of the surface that is detected by InSar. In that case, it was a very, very big signal. It was several, I think, 40 centimeters over 3 years.
Oh, wow. Wow. Well, we've got just a couple minutes left. I see one other question online, which I'm seeing nobody in person, so I'll go ahead and take this one. I have a question regarding earthquakes. Quite a few larger or moderate sized earthquakes does not produce significant deformation, either due to their deep depth or limited magnitude. Do you think your phase interpolation algorithm will substantially increase the signal to noise ratio of noisy earthquake deformation data, for example, in South America forest areas?
Yes, and I think that actually my answer is it's a challenging scenario, but it's definitely doable. So a lot of the work in order to use the phase reconstruction effectively increase the number of interferogram you could use. So the idea is for a large earthquake, you just need one interferogram with one acquisition from the beginning, one after the earthquake, right? That spans the event, and that's all you need. And you can see the fringes, and they have a substantial signal noise ratio. And for the PhD work, we are trying to detect a silent earthquake called a slow slip event, which is also a transient motion, but it only leads to a maximum of 7 millimeters of line of sight motion in that case. So you can think about that as a very, very small earthquake. And the way to do that is if you could have enough, like a 10 SAR acquisition prior to the earthquake, 10 acquisition after the earthquake, and you could form 10 independent pairs that contain the same signal. And as long as they don't decorrelate, you could actually maintain the coherence because they tend to decay over time and become random. As long as we can use the phase reconstruction to maintain coherence with many acquisition, and just by simply average all those interferogram will give you a much cleaner signature because the signal tend to be consistent over all this pair. The noise are typically random.
Well, if I may, let me kind of expand on that question because I'm kind of curious. You know, and forgive me if I use not quite the right nomenclature, but I mean, have you identified certain areas of the world that you just don't have enough of those quality data points? Like I could imagine, for example, like in the question, right, from Jia, right? There's just massive forested areas, right? And they span hundreds of kilometers, right? So have you identified certain areas that you just really still can't use this technique?
I believe there are areas, so that's why like my group always trying to focus on undersurveyed, challenging area. That's kind of what our group does. I won't say we are able to do global mapping yet, but we're definitely go towards that direction. And also actually in terms of forest area, that's considered even probably more densely vegetated than the Gulf Coast. And so I see there's promising after the launch of NISAR because that is an L-band mission. Right now, what we're doing is a C-band mission. So when you have those different wavelengths, so you can use them for deformation analysis. They still works more or less the same way. You can use the same toolbox. But there's one key difference is that L-band have a little much higher penetration depth. So over the forest area, if you have C-band data, the radar signal going to scatter from those tree branches, which tend to decorrelate, so they have leaves on that. If you have even smaller wavelengths like X-band, they would actually scatter from the top of the canopy. But the L-band typically with 24 centimeter, they're actually going to be able to penetrate through those tree canopy. Their reflection is mostly from the tree trunk, which actually is.
Wow, nice, interesting. So NISAR is exciting opportunities on the
vegetated forest area. And we did some preliminary analysis in Solomon Island, which is a highly active subduction zone. We have an active collaboration with UTIG on that. And what we have found is indeed you can have a very coherent phase measurement using L-band data. Tropical, a lot of trees, but yeah.
Fantastic. Well, one more round of applause for Ian, please. That was a great talk. Thanks everybody for coming.
Thank you.